Hello, I'm Dr. Christian Voyer with Safe Engineering Services and Technologies, and today we're going to be talking about selecting the appropriate grounding software for each project, going from and well beyond the classical grounding equipotential assumption with SES software. In today's presentation, I'll first go over what it is we are trying to achieve with the grounding design, and then briefly go over the workflow of a typical grounding analysis. I'll then move on to the core purpose of the presentation, which is to describe the three major levels of sophistication in performing grounding analyses. And then I'll motivate their existence by looking at a real-world example. The example will demonstrate that the increasing levels of sophistication yield very different results. So what we are trying to achieve is to safely dissipate current through a metallic structure in contact with the soil, most often a substation grid. The sketch here shows a typical case where we need to analyze the east central substation grid fed by three external sources. Under steady-state conditions, especially if the phase currents are balanced, very little current flows into the soil. Under fault conditions, in which there's an unwanted short between the phase wire and the grounding system, to which the shield wires are typically connected, a very large amount of current flows through the grounding system and into the soil. This is the worst case that most often needs to be studied in detail. Current flow leads to a change in electric potential. The resistivity ρ of a material in units of ohmmeters determines how well that material conducts current. Ρ is basically the proportionality constant between the current density and the electric field. A simple example is a cylindrical resistor energized in DC. The resistance between the two electrodes is simply ρL over A, where L is the length of the cylinder and A is the cross-sectional surface area. The voltage drop also along the cylinder is linear. Suppose now that current flows from one grid embedded in soil to another grid embedded in soil. The fundamental equations are the same, but the solution is far more complex because you lose a lot of the symmetry. Even though the resistivity for conductors is much smaller than for soil, given the size of these grids, it will also have an impact on the results. We note as well that the impedance of conductors will increase as the frequency increases away from 0 Hz. What we call the soil structure, how the various soil layers of varying resistivity are laid out, will determine how the current leaks into the ground from a given conductor arrangement. The current injected into the ground by the grid will then lead to a change in potential on the surface of the soil above, but also well beyond the grid boundary. I mentioned at the beginning that the goal of proper grounding is to safely dissipate current. What we mean by safe is to reduce the touch and step voltages to some tolerable level. Standards like IEEE 80 will use a conservative equivalent body resistance and some physiological data on how much current the body can withstand for a given duration, and from that we'll determine what the tolerable voltages are. We define touch voltage as the difference in voltage between a point on the soil surface, where a person's feet would be, either V1 or V2 in the diagram, and some metallic object. The metallic object doesn't need to be directly attached to the grounding system. Even buried metallic objects near a substation grid can lead to high touch voltages. One common example is a long fence. Step voltage is defined as the voltage between 2 points on the surface of the soil, say V1 and V2, at some maximum separation distance, usually around 1 meter. For equipment integrity, it may also be necessary to keep the voltage with respect to remote earth, the GPR or ground potential rise, below some given value to avoid problematic stress voltages. So now that we know what results we're looking for, let's see what we need to do to get there. The first step is to obtain an accurate representative soil model, because this is the medium in which current is being dissipated. If the soil model is not right, the grounding model will definitely not be right. The best way to measure soil resistivity down to the appropriate depth, which is somewhat at least as deep as the diagonal length of the grounding system under study, though that does vary depending on the soil model being derived, is to perform a 4-probe measurement. Basically, we're injecting current into the ground, and we measure the potential difference between 2 points on the surface of the soil, and we do this for various distances. We can then perform a curve fit on the results using our soil measurement analysis module, RESAP, to obtain a multi-layer soil interpretation. It's this derived soil model, the various layers, their thickness, the resistivity, that we will use in our grounding model. One aspect of the fit I'm showing here is that the data can only be accurately represented with a 3-layer soil model. If we restrict ourselves to a 2-layer soil model, we're either overestimating the bottom resistivity layer or we're overestimating the top resistivity layer. The layering of the soil doesn't only affect the calculated grounding impedance, but it also strongly influences the surface potential profile. Here we can see that if the resistivity of the top layer is much higher than the bottom layer resistivity, for conductors in the top layer, the current will rapidly try to access the bottom layer. And for conductors that cross the boundary, they'll mostly leak their current into the bottom layer, not the top. The opposite effect is true if the top layer is more conductive. Current will spread out much more horizontally, though it will always eventually go into the bottom layer. This is also going to change the potential profile on the surface of the soil. One last very important aspect of soil modeling is that it's absolutely essential to have true multi-layer calculation capability, because uniform or 2-layer soil models are rare or inexistent. Here are some results from a soil measurement survey done in Ireland, where basically 81% of measurements yielded 3 or more layers, and none were found to be of uniform resistivity. With a reliable soil model, we can now create a first grounding grid design to obtain a grounding impedance. Using that impedance, we can then perform a fault current split calculation. For transmission lines feeding a fault at a substation, if there are shield wires present, not all the current will be injected into the grid. Rather, the current will split between going into the soil at the substation and going back to the source via the shield wire, or in the case of a cable, the cable sheath. Considering this effect will greatly reduce the fault current at the substation, especially since inductive coupling between the phase and shield wires helps push current along in the opposite direction of the fault. In the case of cables, the effect can be quite strong, leading up to 90% of the current not going into the substation grid and going back to the source via the sheath. Knowing precisely how much current is injected into the grid and how much returns via the shield wire or cable sheaths, we can now obtain the potential of conductors and the potential of the soil in detail, and with our design limits on hand, determine whether the design is acceptable or not. It's the grounding calculation that is the core purpose of the presentation. The first level grounding calculation is referred to as classical grounding. This is what we call MultiGround at SES, and the grounding module is called MALT. At this level, the grounding calculation assumes all conductors are equipotential. This means that they're basically superconductors energized in DC. The reason the assumption is made is because it frankly just makes the calculations far simpler. The material characteristics of the conductors are completely ignored. Only the potential due to current flow in the soil is calculated, meaning that we only need the outer radius of conductors. One important consequence of this is that the calculation cannot consider the exact fault location. Considering different fault locations here, the resistance along conductors from one point on the grid to another is null, so the exact location of the fault will not change the results. We refer to cases in which this is a healthy approximation as electrically small. This is true when the grid is relatively small and the soil resistivity is moderate to high. It's basically a competition between how easy it is for the current to travel around the grid versus how easy it is for it to leak into the soil. In many cases, the approximation is valid, but as the size of the grounding system grows and the soil resistivity drops, we need a more sophisticated approach. The second level grounding calculation we refer to as extended grounding. This is what we call MultiGroundZ, and the grounding module is called MALZ. At this next level, we consider the complex impedance of conductors and can therefore calculate the potential drop that results from current flowing in those conductors. We therefore consider the inner and outer radii of the conductors, the characteristics of the conductor material, and the frequency of the AC current. With the conductor impedance modeled, we can now accurately consider the effect of the exact fault location, since the impedance between points in the grid is no longer null. Not only can we now be sensitive to voltage drops along conductors, but we can also model circulating currents in the grid. An additional useful feature is that we can model EMFs on conductors from a source of inductive coupling, though the magnitude of the EMFs needs to be computed elsewhere. The improvement means that we can now essentially accurately compute any size grid in any soil, even in frequencies up to 1 megahertz. Thus far, we've focused mostly on conductive coupling, the idea of current flowing in the soil and along buried conductors, with only a passing mention of inductive coupling that we mentioned in the context of fault current split calculations. The next way to improve the grounding model is to solve the electromagnetic equations completely in order to get all electromagnetic interactions represented. This is what can be done with MultiFields via the HIFREQ module. And by the way, the high frequency capabilities in MALZ and HIFREQ certainly don't prohibit using them at very low frequencies as well. Solving the electromagnetic equations means that inductive coupling is now taken into account. Of course, so is capacitive coupling, though for fault studies it's less important. Inductive coupling results from a longitudinal AC current causing a time-dependent magnetic field, and conductors nearby will develop an EMF along their length, which is going to impact how current flows along them. The magnitude of the EMF will depend on the length of the parallelism and proximity between the conductors, the magnitude and frequency of the current, and the medium in which the magnetic field is propagating. In a grounding grid scenario, inductive coupling can result from coupling with above-ground conductors, but can also be a factor due to adjacent current-carrying conductors in the grid itself. The enhancement means that now it's meaningful to include far more detail in the grounding model, such as above-ground structures like bus bars or nearby transmission lines paralleling the grid, or a substation fence, or concentric cables, as we'll see later. The electromagnetic fields approach is the most sophisticated and complete approach. Let's take a quick look at an example that highlights the difference between an electrically small and an electrically large grounding system. Here we have a simple rectangular grid in 100 ohm meter soil. At 140 meters by 280 meters, it's a decent sized grid. Here we suppose that there's a 1 kiloamp fault on the left-hand side of the grid. If we look at the potential profile along the bottom edge of the grid, we can see that in this case, the equipotential assumption fares pretty well. The MALT, MALZ, and HIFREQ results essentially match. Already in this example, though, we can see that MALZ and HIFREQ are detecting a slight asymmetry. The blue line is slightly higher than the dashed line on the left, and slightly lower on the right. This really highlights how there really is no such thing as a perfectly equipotential grid, though in this case it matters little. Reducing the soil resistivity to 20 ohm meters and increasing the conductor impedance changes the result dramatically. Not only in the magnitude of the potential, but also in the profile shape, it's drastically different between MALT, MALZ, and HIFREQ. The treatment of the soil is basically the same. All three modules accurately consider multilayer soil, but the fact that MALT considers the grid to be perfectly equipotential is quite problematic in this case. In practice, it can be quite hard to predict in advance whether or not the grid will be reasonably equipotential. The prediction is made particularly hard in multilayer soil with high resistivity contrasts between layers. On top of that, it's hard to be reasonably conservative. In the case I'm showing here, the soil potential is overestimated on one side and underestimated on the other. Even without changing the soil resistivity, we can see differences between the results reported by the various modules in the case of a large grid. Here we have another simple example based on a real project performed by SES. The grid is fairly large at 2,000 by 1,000 feet, and the soil resistivity is on the slightly low side at 50 ohm meters. The fault and circulating currents are quite large at 63 and 40 kiloamps, leaving an earth current of 23 kiloamps. Model A represents the MultiGround or equipotential assumption model using the MALT module. Only the total earth current is specified, and that with no specific location. Model B represents the MultiGroundZ or extended grounding model using the MALZ module. Here the total fault current and transformer return currents are specified at the appropriate locations 180 degrees out of phase. The net earth current still works out to be 23 kiloamps as the program will determine, but the circulating current is included in the model. Model C represents the MultiFields or electromagnetic field theory model using the HIFREQ module. In this case, we inject 23 kiloamps from the outside of the grid above ground and specify that a total of 63 kiloamps is injected from the bus. Again, the net earth current will be 23 kiloamps, but this time the program will determine the circulating current and take into account the induction caused by the longitudinal current flow in the bus bar above ground. Looking at the results from Model A, we again see a very symmetric result, as expected with an equipotential grid. The highest touch voltage of 575 volts is at the corners, also expected with an equipotential grid. Taking into account circulating currents breaks the symmetry of the results. The highest touch voltage of about 2 kilovolts occurs near the highest current injection. We also see another local maximum near the transformer return location. The large circulating current can actually cause a large potential difference between various points in the grounding system. Looking at the complete model, we see a pattern qualitatively similar to Model B, but the maximum touch voltage is now closer to 1.5 kilovolts. Modeling the case with as much precision as possible not only greatly influences the results, but can reduce material costs by up to 50%. In the realistic scenario that this example is based on, a project with Manitoba Hydro, the cost of the grounding grid being considered was reduced from $7 million to about $3.5 million, a significant savings indeed. Let's now take a look at a more realistic analysis, a more complete analysis that'll highlight more of the differences I've been talking about between MALT, MALZ, and HIFREQ. The project we're going to be looking at in more detail is a grounding study of a gas-insulated substation, or GIS. Older substations are constantly being upgraded, and GIS equipment can be used to save space. The GIS installation needs only 10 to 25% of the land area required for conventional equipment, though the fault levels remain similar to conventional substation arrangements. This means that we have far less area than usual to dissipate the current safely. Because the current-carrying phase conductors now have the GIS enclosures in very close proximity, induced currents can be substantial and lead to significant voltage drops along the enclosures. Of course, this could happen between the enclosures and the ground conductors as well. We therefore need to study an additional fault scenario in which there's a flashover between the bus conductor and the inner wall of the enclosure. The above-ground bus bars are parallel to ground conductors as well and can lead to inductive coupling with ground conductors when our grounding system is large. Also, when a large amount of circulating current exists within the substation, it's also flowing along the above-ground bus bars from local transformers to the fault location and then returning back to the sources through the ground conductors. The currents, along with the induction they lead to, will cause noticeable potential differences within the grid area. Given the space restriction, the grounding design can be challenging. Frequent bonding and grounding of GIS enclosures is going to be needed to minimize hazardous touch and step voltages within the GIS area. And additional grounding measures to include the use of massive reinforced steel rebar in the concrete foundation of the GIS building that are connected to the GIS grounding system. The case we're looking at today is a substation covering an area of approximately 1,100 feet by 650 feet. It functions as both a medium voltage distribution substation and a high voltage switching station. The operating voltages are 13.8, 34.5, 99, 115, and 230 kV, and the future 500 kV is also taken into consideration. On the right is a plan view of the grounding system. The top half part with denser conductors is the GIS area, highlighted in orange in the image, and the bottom wider part is the existing grounding grid. The above-ground bus bars, which pass over almost the entire grid, is shown in green. If you want to read more about this case, it was actually published in 2012 at the 5th China International Conference on Electricity Distribution. The title of the paper was Gas Insulated Substation Grounding System Design Using the Electromagnetic Field Method. As we discussed in the workflow portion of the presentation, we first need a reliable soil model. In this case, we used a 3-layer soil model, and as I explained earlier, with such resistivity contrasts, using the top 2 layers or bottom 2 layers only would either lead to an overestimate of the top layer or the bottom layer. In this substation, there's actually a wealth of overhead shield wires and grounded transformer neutrals that are connected to the substation grounding system, and they provide many locations where the fault current can enter or exit in the grounding grid and circulate within the ground conductors. The next step is to perform the fault current split calculation. The numbers are quite staggering, but it's important to properly parse what's going on. First, a total of about 61.5 kiloamps are injected into the grid though 43.7 kiloamps are actually circulating or returning currents. In the end, only 17.8 kiloamps will be discharged into the soil by the grid, though we expect the 43.7 kiloamps to have their say. Depending on the sophistication of the model, we'll soon see that the simpler methods ignore rather large portions of the fault current, and their effect can be substantial. With the soil model that gives us a top layer of 150 ohm meters and using the X/R ratio of 20 for the system, as well as the 0.4 second fault duration, we can calculate an acceptable touch and step voltage according to IEEE standard 80. Crushed rock certainly helps raise the tolerable voltage limits because it basically acts as an additional insulation on the feet, but it can't be used inside the GIS building. Now that we're familiar with the case being studied, let's take a look at how each level grounding solution fares. Let's start with the classical grounding module, MALT. Because we're using the equipotential assumption, basically we're only computing how the current flows into the soil and not along conductors, we know that we'll only be looking at below ground metallic structures, and that only the outer radii of conductors will be taken into account. In all, the model includes the main grounding grid conductors, the massive reinforced steel rebar, and the substation fence posts. Since the conductors have no impedance, the exact fault location is not taken into account. Let's take a look at the model in our grounding model graphical editor, SESCAD. So now we open our classical grounding model. Input files in SES software use a two-letter prefix that corresponds to the program in question. So here we're using the MALT module, so we see the MT prefix. So let's drag and drop it into SESCAD and take a look. We've got a nifty ambiguity viewer here that can warn us about potential problems in our modeling. There are no ambiguities here, and I'm not going to edit this model, so I'm just going to close this like this. And let's zoom to all. Here you can see the grid that was sketched earlier in the presentation. The dashed lines you're seeing represent profile points, basically locations where we want the program to calculate the soil potential because we'll need those values to calculate step and touch voltages. Using the quick info tool here, we can see that the spacing between points is a little shorter than 1 meter in order to get the most accurate step voltages. Basically, in this calculation, we want to be able to report touch and step voltages everywhere, even a bit outside the substation area. In fact, we can measure exactly how far out we're going. The measurement tool here. So we're going at least 44 feet out from the outside of the grid. For touch potentials, we'll probably be reporting only up to 1 meter outside any conductor that can be touched, like 1 meter outside the fence. For step potentials, however, it's important to know that the step potential has gone down a prescribed limit even as we walk away more than 1 meter away from the substation fence. To see the grid conductors better, we're going to hide the profiles display, and we can see the conductors far better now. As I mentioned before, we're only seeing above ground conductors. We can take a side view just to see that no conductors, I'm zooming in with the mouse wheel here and panning, no conductors are above grade. Let's go back to a top view and let's zoom in to the GIS building. Let's get some information about the conductors that we're using. Again, with the quick info tool here, we just hover above one of these rebar conductors. Other than positioning information, we really only have the outer radius of the conductor specified. Looking at the grounding conductors, we see a very similar definition. Basically, the MALT model does not distinguish between steel and copper, only the outer radius of the conductors. One quick note about conductor segmentation or subdivision that you're seeing here. We do need the conductors to be sufficiently segmented for the results to be accurate, but in a grounding model such as this one, the program is going to automatically segment conductors at every intersection. So this model is plenty accurate with the default segmentation. Using the measurement tool, we can get some ideas of the dimensions of the model here. The GIS building is approximately, let's see, 40 feet by 200 feet. You can zoom in, get an idea of the rebar mesh. So it's about 4 feet by 4 feet, it seems. This is actually a conservative value since in reality the mesh is usually far tighter than this. The mesh size of the grounding grid area is considerably larger at about 15 feet by 15 feet, or 14 feet in this one. We can get an idea of the depth of the grounding grid by looking at the Z coordinate. Here it's about 1 foot. Elsewhere, yeah, it's pretty much 1 foot. By tilting the view, clicking on the airplane, clicking and dragging with the control key, I can tilt the view. Move this aside. We can actually see vertical conductors. We should have ground rods and fence posts. Highlight this and see. So here we have a 10-foot ground rod. The fence posts are a bit shorter, at 4 feet long. As I was saying before, we don't have conductor types, but we do have various radii. So let's look at the radius distribution here. We have a nifty filter by radius that will color conductors according to this filter legend color scheme based on radius. You see the rebar, the grounding conductors around the GIS building have a different radius. Several radii used in this model. Taking a side view again, we can see how the soil model and our grid live together. So let's label the soil data. We can zoom in here. And so we see the top layer of 150 ohm meters. That includes actually a majority of the grid conductors. But the rods penetrated to the 320 ohm meter layer. And far below, we see our 90 ohm meter bottom layer. Returning to our top view, the energization is specified globally for the main electrode, since we don't specify a specific fault location. Notice that there's no angle specified on the fault current because, again, these are like superconductors energized in DC. There's no point in specifying an angle, nor is there a frequency specified. The program won't be using that information anyway. So let's take a look at the results from this run. Given the broad complexity of the model and the wealth of results produced by it, we're going to focus on the touch voltage in the GIS building area to see the impact of the various levels of modeling precision. We can go to Run Reports and select View Results. We're interested in results that involve the observation profiles, so we select Computations Plots, where touch voltage is default selected. We want to zoom into the GIS building, so we go to Advanced. Check the Define Zoom area and use the Visual Zoom selection. Progressively zooming in, I can select just the GIS building area. Oops. And plot. So we see a maximum touch voltage value of 13.94 volts, which is promising since it's well below our target limit of 213, though keep in mind that it's likely that the grid is overperforming. We'll have to see the other models to gauge exactly how well the equipotential assumption fares. So now we move on to the next level model. We'll start with a simplified extended grounding model with the MALZ module. Again, only below ground conductors are being modeled, and we'll find many of the same elements as the previous model, the key difference being that now we'll include conductor characteristics. Also, we'll be able to consider the exact fault location. For illustrative purposes, I'll present results for faults just outside the GIS building and inside the GIS. As a first step, suppose we consider only the net fault current, or earth current, being injected into the grid. We're not yet going to consider circulating currents. Let's take a look at the model in SESCAD. So now we're no longer in classical grounding, we're in extended grounding, and we'll look at the net current example. Before we begin, I want to just mention that the frequency is now an editable quantity. Again, I'll hide the profile so that we can see the conductors better. Okay, so first and foremost, the conductor type filter is now available. By the way, the default conductor is kept to have the resistivity and permeability of annealed copper. So in this example, we have black solid coppers, 350 and 500 kc mil stranded coppers, 4/0 stranded coppers, stranded copper wire for the fence ground wire, and the reinforced steel rebar in the concrete foundation of the GIS building is being modeled as steel. The resistivity of 12.1 relative to annealed copper and a permeability of 250, relative permeability of 250. Now, the energization is no longer global. There's an exact fault location, and the way we define it is to attach to a conductor a given energization bus. We can find the energization by filtering for it here. Let's select it to be able to see it a little better since the conductor is too small for the red highlighting to show. Change the highlighting method here. Select the faulted conductor. We can select it here. We see that it's at the northeast corner of the GIS building. We can quickly load the other fault that we're considering. Again, hide the profiles to see the conductors better. Filter for energization. And select the faulted conductor. So here we're outside the GIS building, but we're pretty close to it. So the fault currents specified are identical, they're just at different locations. Let's take a look at the computation results. So injecting only the net fault current just outside the GIS building, the maximum touch voltage is 23.1 volts, which is already quite different than the previous result. Faulting inside the GIS building gives yet a different result of 86.4 volts. So now not only is it different from the equipotential assumption, but the fault location matters as well. This is not too surprising when we consider how much poorer a conductor steel is to copper, and here the current is injected directly into it. But as I said earlier, we can actually do better than the net fault current injection in MALZ. We can take into account circulating currents. So we're going to add the shield wire return locations and the transformer neutrals. So looking at these new models in SESCAD, total currents. The grid design, again, is the same, but it's the energization list that is going to be much longer. The total fault current is represented as expected, and the shield wire returns are flowing roughly in the opposite direction as the total fault current. We also see substantial currents going into and out of transformer neutrals. We can see that the shield wire returns are at very different locations. So again, hiding the profiles so we can see the conductors better. Here the selection of the conductor is prohibited because it's part of a group, so let's just ignore the group for now. And we see one return, another further away, and let's see here, completely on the other side of the grid as well. The same is true for transformer neutrals. It wouldn't be surprising, therefore, if circulating current could have a strong effect on results, given that so much current has a fair distance to travel. Looking at the results continues the theme we're on. They're different. Here we have all the relevant current injections and extractions at the right locations, shield wire returns, transformer neutrals, and so for a fault just outside the GIS building, our max touch voltage is now 63.2 volts. And for the fault inside the GIS building, we're now at a staggering 256.2 volts. Adjusting the accuracy of the model is certainly changing our perception of safety in the substation. The final and ultimate enhancement to this model is to perform a full field theory calculation, including all nearby conductors and have as accurate a representation as possible of the currents flowing in them. We therefore include all the above ground structures like bus bars and the GIS structure. The GIS structure is actually essential since we're responsible for ensuring the safety on the enclosures. Enclosure and gas insulation on the face conductor is represented as a concentric cable in the HIFREQ model. The fault current is also more specifically specified in this model since now we will be tracking the effect of current flowing in the bus bars. Each fault contribution is listed independently rather than the total fault current. The whole purpose of this model is that finally all electromagnetic interactions are present. Specifically, the addition of induction in this scenario is going to have a substantial impact. Let's load the HIFREQ model in SysCAD. So we're no longer in extended grounding, but rather EM fields grounding. If we take a perspective view, tilt a bit, the difference between this and the other models is immediately apparent. We have above ground structures. Taking a side view, we can see the above ground structures clearly. Zooming into the GIS area, again hiding the profiles to see the conductors better. The dashed lines here represent cables. With the filter tool, we can see which cable types are used and where. To see the full definition of the cables, we open the Cable Types interface. We have two different radius enclosures defined. Here the enclosure is defined to be the sheath of this cable and is not insulated. We have a 12-inch radius enclosure and a 7-inch radius enclosure. The underground 230 kV cable has a core sheath and armor, and the armor conductor is insulated. The enclosure is grounded at its two ends, outside the GIS building, but also grounded densely, maximum 8-foot separation distance, at various locations along the length. Just for your information, though we don't use them in this model, HIFREQ can also model pipe-type cables, where you can define multiple multi-layer cables inside of a single enclosure. Cables and their components are connected to each other and with regular conductors using virtual connections. So we can go to the virtual connection layer here, and they'll appear in blue. These are basically perfect connections used to simplify connecting the various cable components. We can connect to any component of the cable, core, sheath, armor, or enclosure. Go back to the main. As I mentioned earlier, the list of energizations has now grown in order to be more specific. The phase wires are now energized at the bus bar level to take into account the induction resulting from current flowing through them. For example, here. Taking a different view here. So for example, this 5.7 kiloamp current won't go directly into the grid, but rather through the bus bar, which leads to induction with the grid, and then at the fault location. The conductor types list is also richer. We include all the conductor types related to the above ground structures, namely the ACSR and AlumoWeld conductors. The fault in this case will be modeled as a simple connection between the faulted phase in question and the grounding system, or the GIS enclosure, and in HIFREQ, anything you want, really. This model is the most accurate and complete depiction of the case possible. So let's look at how it impacts the results. So for the complete model for a fault just outside the GIS building, we now have a maximum touch voltage of 45.4 volts, a result that lies between the values obtained with the lesser models. For a fault in the northern part of the GIS building, our max touch voltage is now 39.4 volts. Again, the result lies between values obtained with simplified models. Putting all the results together side by side, we really see that the accurate results cannot be predicted from more approximate models. Simpler does not mean either consistently more conservative or optimistic. The only truly reliable way to get correct results is to have the most sophisticated model possible in this case. So let's summarize what we've learned about grounding calculations today. It's important to have models that are as complete as necessary. Conductors are not perfect, and current flow can cause a substantial potential drop along them, which in turn can change touch and step voltages. Induction in close quarters can be strong and will also change touch voltage results. We've also seen that approximate models are not only not optimal, but cannot be guaranteed to be conservative. The results change we see when including more interactions is not uniform in shape or magnitude. There was a case we saw early in the presentation for which the equipotential assumption actually worked quite well, but it's important to ensure that the calculation methodology is sufficiently complete for the case at hand. Cutting corners could lead either to costly overdesign or an unsafe optimistic design. So for small grounding systems and moderate to high soil resistivity, one can use the equipotential assumption with the MultiGround software using the MALT grounding module. For larger grounding systems, especially in low soil resistivity, it's imperative to consider the impedance of conductors with the MultiGroundZ software using the MALZ grounding module. And when inductive coupling is substantial and cables need to be modeled accurately, the MultiFields software using the HIFREQ grounding module is best. Note that HIFREQ can also include transformers in the model. You can visit the SES website to learn more about each module and see how SES software can also be used for lightning and electromagnetic interference studies. You can contact us by email at info@cestech.com if you have questions about our software or services. And finally, SES offers a broad range of training options for grounding, lightning, or electromagnetic interference studies via either our standard course or fully customized training. Thank you for your attention.